Now, there's another question that arises. Here you are, you're out in the lab. You stick thermocouples in. All right? All right, we'll stick a thermocouple in somewhere. Here it is. It measures the temperature. What do you think about that temperature? Don't come and tell me that's T average. There's no reason for you to believe that's T average. Tell me that's T average, swoosh. Okay, so we got a lot of approximations going on now. So let us begin our calculation. Our calculation requires us, okay, we'll call something called W is equal to the mass flow rate pounds per time times the heat capacity in heat per pound per degree. So W is a product of a mass flow rate and a heat capacity. So I will write, for the tube, I will write W dt dz equals U P for the perimeter upon which the heat transfer coefficients are based, T star minus T. I'll call the temperature in here T and the temperature in here T star. T is the average temperature in here, T star is the average temperature in there. The U's are based on those. So this is what I write. Now I need one for the other phase, W dt star dz equals, this will be W star. So I got a flow rate W here and a flow rate W star there. Flow rate W here, flow rate W star there. So like W star, again, U, P, T star minus T. So here's where we have two equations and two unknowns that we might like to solve. Do you remember how this is done? There's sort of a smooth move here that you can use sometimes and not other times. What do you think a person would do with this problem? Well, if at all possible, you ought to always reduce it to one equation and one unknown. If you can, reduce this to one equation and one unknown. So we can do that. Thing to do is to divide this one by W, divide that one by W star, subtract that way. And you have, I think you must have remembered this game, dt star minus T over T star minus T equals U P dz divided times 1 over W now. Yeah, it must be W star minus W. You integrate both sides. What do you get? You get the log, okay, we're going to integrate from z equal to 0 to z equal to L. So you get log of T star in minus T out over T star out minus T in equals UA 1 by W minus 1 by W star. And you also have the balance equation. You have this and one more equation. You have W star, T star in, minus T star out equals W, must be T out minus T in. These two equations solve your heat. Yeah.
Is E perimeter?
Yeah. So perimeter dz is area. Okay, well, dz integrates into L. Perimeter times L is A. So I must have written A here. Yeah, right here. This A is basically the perimeter times the length, okay? So, we will come back and talk about this a little bit, but we're going to put the co-current equation up here, and then we're going to ask you a question. Let me tell you what the question is. I want you to come prepared to discuss this. Here's the question. We're going to do the co-current case. The question is, suppose I'm doing a countercurrent case and a co-current case. Is the countercurrent case always better in some sense?
Yeah.
Is the question.
Yeah.
Good for you. That's what I think you all will say, I hope, because that is wrong. No, but good for you, because I'm sure that's what you've been told. Okay, you ready, AJ?
Yeah.
DJ. You know, it's a shame